Hi, sir.
Hi, Amy. How are you doing?
I'm good, thank you. How are you?
Very good, very good. So, how is your mathematics classes going on?
Good. Yeah. I got one of my tests back yesterday,
Hmm.
and yeah, I got 88%.
That's good.
So it was good. It was just there was one question that I didn't get time to do. So I think timing is also a skill, not just knowing the content.
Yes.
So yeah, I could obviously answer that 5 marker really easily. It's just that I just needed the extra 30 seconds. That was all. Like that's how easy the question was.
Correct.
But yeah, I guess I'll just have to work on timing now and doing it in time
Yes, yes.
conditions.
That is very important. Yeah. And secondly, we should not waste time on some things which are right. Sometimes we overthink, and we should not be overthinking. That takes
Right.
up a lot of time in a test paper. So I think that is kind of
Yeah.
important. And you learn, you lost, some marks because of the time constraints. So
Yeah.
it will be good for our future, right? Okay, great.
Right.
So we'll actually continue with mechanics and we'll talk about the basic formulas, which are for constant acceleration. Are you ready for that?
Yes, I am.
Okay,
Let's go.
great. So let me share the screen with you and we'll take from there. There you go. So what I've done is, because most of the material is there in your book itself, so I thought I'll have a slightly different approach while going through the lesson, right? So today
Yeah.
we are going to discuss constant acceleration. So whenever you have the condition for constant acceleration, that really means that there could be a velocity, right? But
Mhm.
velocity is kind of linear. So if you draw a tangent on the curve of the velocity, it will be constant, correct? A linear curve,
Right.
or if you draw a tangent, the slope is or the gradient will be same at any 2 points on the curve, correct? So when we say constant acceleration, it also implies that the velocity is linear. You get the idea.
All right.
This
Okay.
is one thing which we have to understand very clearly. Velocity
Hmm.
could be zero also, but if it is like moving, in that case, the velocity is linear. So if you draw the graph of velocity and time, you'll get a straight line, which you can see on the screen, right there. Do you see that? So on this particular
Hmm.
line, if you take any 2 points, right, anywhere, any 2 points, the gradient will be the acceleration, correct? So that gradient was going to be constant because the slope of the line is constant, right? So you get acceleration, which is constant, shown as a horizontal line on the graph of acceleration and time,
All right.
right?
Hmm.
Now, those who have done calculus, they understand that if the velocity graph, which is the rate of change of displacement, is a straight line, then rate
Hmm.
of change of displacement should be quadratic in nature, as shown here. But well, if you have not done
Right.
calculus, in that case, we'll try to prove it using derivation of the formulas. Okay?
Okay. Yeah.
So today, we are going to begin with the very basics. Right here, you can see what is velocity. Velocity is rate of change of position, correct? So we write delta x over delta t. In my calculations, I'm using the variable s, lowercase s, for displacement, which is change in position. And delta t, sometimes I'll
Hmm.
just write t if the initial time is zero. Many times,
Right.
in our cases, we have initial velocity zero, initial position zero, initial time zero. So in that case, I'll not write delta t, but I'll write just t, right? So let's
Yeah.
be clear on this. Displacement also, where when I write only x, it will be from 0 to x, that displacement. Is that clear to you?
Yeah.
Okay. But well, in the formula sheet, when we talk about acceleration now, it is rate of change of velocity. So delta v over delta t, right?
Hmm.
Average velocity is another term which you should be familiar with. Average between any two is starting and final, initial and final velocity divided by 2. Just add them up and divide by 2, just as you take average of anything, correct? So that
Yeah.
is average velocity. Now, displacement can also be treated as time into average velocity. Let's say a car is moving at 60 kilometers per hour and then it picks up speed, becomes 70 kilometers per hour, then 90 and 100 kilometers per hour. And the whole journey of, let us say, 2 hours takes place within some duration, the whole journey of, let's say, 2 kilometers takes 2 hours, then we know what the average velocity is. So using this average velocity and the time taken, we can find the final distance covered. If we are doing from 0 to the x value in a straight direction, that is same as the displacement also, correct?
Yeah.
So displacement can be written as average velocity into time if it is in one direction only, no turns, right? Displacement, let me
Mhm.
remind you, is a vector quantity, correct? So direction is important. So in these calculations,
Right.
we are saying if we use the term distance and displacement, we'll assume the distance is along the same direction, right? So only then displacement and distance will be same. Otherwise, they are two different things, correct?
Yeah.
Now, for constant acceleration, these are the formulas which you must have read and come across. V equals to u plus at, s equals to ut plus half at square, v square minus u square equals to 2as. Another variation to s equals to ut plus half at square, which is in terms of initial velocity, is in
Mhm.
terms of final velocity, which could be written as s equals to vt minus half at square. So we'll also see the derivation of these formulas in today's lessons, okay? And we'll take up some word problems.
Oh,
Yeah,
I just wanted to say, when I remember last lesson you saying we always needed u to find, like, to solve any of the equations, but in the last one that you've put there, it doesn't have u. So
correct.
is
So
it?
because we know v can be written in terms of u, v equals to u plus at. Do you see that part? So to find,
Oh, so you
we have
could
a
just sub
formula.
in,
You can sub in. That's
right?
what we have done there.
Yeah.
That's
All
what we
right.
have done.
Okay.
Correct? So u becomes v minus at, and that negative term you can see here in half at square. You get the idea?
Oh,
Yes,
right.
you are right. So when we were solving questions last time, it was necessary to
Mhm.
find u, right? Only then you get the
Right.
final velocity terms, right? Uh,
Yeah.
Perfect.
That makes sense. Yeah. Because the way you said it, when you sub that in, then you would get minus.
Then you
Yeah.
get
I was going to say, where did that come from? Right.
perfect. Well,
Yeah.
good student. I like that. Correct. So what we have done here is we have modified the formula itself so that you could use even with the final velocity, and that's the whole idea, right? But this formula is very rarely used. Most of the students are not using
All
this,
right.
right? But it's a good to know. Good to know. It
Yeah.
can save you time in test papers sometimes, you know?
Definitely need to know that.
Yes. And
Oh.
then we will take us some questions where there'll be different stages of displacement, velocity, and we'll work out what is their numbers. Okay. Let's begin with the
Mhm.
derivation first. Okay. So we'll talk about constant acceleration and velocity relation as we began with. So as you know, acceleration is rate of change of velocity, correct? So if I have a graph which represents velocity with time, then gradient of this graph will give you acceleration. We are saying that constant acceleration means the graph of acceleration should be a straight line, constant at each and every point on the velocity time graph. That implies
Right.
that the velocity time graph should be linear. Is the clear, right? So this
Right.
is the
Yeah.
first part to understand. So when we say acceleration is rate of change of velocity, when acceleration is constant, the rate of change of velocity is constant. This
Mhm.
implies that velocity time graph will be a straight line. Do you get this?
Okay. So when acceleration is constant,
Yes,
the rate of change of velocity is constant.
constant.
So that means the gradient is
Yes, constant.
constant. That's why that acceleration was constant. So that means the velocity time, like the line you draw, should be straight
Yes,
without any
because
curves.
only this line will give you the constant gradient. Do you see at every point?
All right.
The gradient
Okay.
is
Yeah.
constant, and that is the reason why velocity time graph should be linear. Very important concept.
Right.
So that is one. Now let's begin from here. So let us say that the initial velocity is u. So we are going to use this symbol u for initial velocity, v for final velocity, right? Instead of using any subscripts that makes things slightly difficult, we'll use u and v. Most of the books will be using subscripts, v initial, v final, something like that, correct? So
Oh,
u
okay. Yeah.
for us is initial velocity, okay?
Yep.
Now it says if u is the initial velocity, so we're defining u as initial velocity, v is the velocity after time t, then acceleration a is the gradient. Perfect. Delta v
Yeah.
over delta t. Change in velocity is final velocity minus initial velocity. Change in time is t minus 0 because we are starting from 0.
Yeah.
And now that v minus u divided by t is equal to a, cross multiply, at is v minus u, rearrange, velocity is initial velocity plus acceleration into time. So that gives us our very first formula to work with for constant acceleration. Is that clear to you?
Um. Yep. Yeah.
Perfect.
Makes sense.
Now let's move on and derive the other formulas. So there are 5 of these very popular formula. Now we'll talk about the average velocity, right? Average velocity between 2 points A and B is basically initial velocity plus final velocity divided by 2. That's how you get average velocity. Now what is displacement? Displacement is time taken to move from point A to B, right? So the displacement will be average velocity into time. Average velocity we know is u plus v divided by 2 times t. That gives you a relation between displacement and average velocity and time. Is that clear to
Yeah.
you?
Mm-hmm.
So we have a formula here. We have already derived one particular formula, which is v equals to u plus at. Now look at it. If I replace, I can eliminate one by one each variable and get 3 different equations. So we'll begin with the very first, where we are going to eliminate final velocity from the formula. So that
Mm-hmm.
really means if I rearrange the formula v equals to u plus at and substitute, I mean, I'll use it direct, u plus at as v for v. Do you see that? So what do I
Mm-hmm.
get? U plus at plus the initial velocity u. Do you see that? So this is my displacement formula. I've replaced this velocity, final velocity, with the term initial velocity plus at, u plus at. So I have u plus at by 2 times 2, t. So we're calling this as our, let's say this is second formula. This is third formula. So this is our first formula, correct? So we are substituting 1 in 3.
Yep.
Then you get s equals to u plus 80. That means 2u. 2u divided by 2 is only u times t. So you get ut plus half 80 square. So you get your formula. Let's call this as our formula number 4. Do you see how simple the derivation is?
Yep.
Just by elimination. Now, in the second case, I'm going to eliminate t. To eliminate t, I'm rearranging v equals to u plus at. So when you rearrange, you get t as equal to what? T will be v minus
V
u
minus
over
U.
a.
Yeah.
So if I substitute that for this t, you see that? Then I get what? Average velocity times v
It's,
minus u over a, correct? And when you multiply,
yeah.
this is sum times difference, product of sum and difference in the numerator, right? That gives you v square minus u square. Cross multiply, you get 2a. So you get your fifth.
Oh, right. Yeah. Yeah.
Got it?
Yeah. That's clear.
Perfect. Now we are going to eliminate u from this equation. Which equation we are talking about? This equation. We are going to eliminate u from this equation. Clear?
Oh,
So
so whenever we
rearrange.
do it, we're going back to the original.
Yeah, we are only working with these 2 equations.
Right.
We're working with
Okay.
these 2 equations, right?
Yeah.
Eliminating one by one each variable and getting a new equation. That is all. So that you can directly use these equations. You don't have to derive them. You get the idea.
Right.
So now we are going to eliminate u, substituting u as v minus at in the same formula of displacement, which is equation 3. So you get S equals to V minus AT, right, plus V, right? So this becomes V minus AT plus V. Divide by 2 and you get your final formula. Let's call this formula number 6. Do you get it?
So yeah, makes sense. So from that one formula,
Yeah.
initially that you did in the beginning, we've just used a process of elimination and then derived the other three. So
Other.
that's kind of, yeah, that was like in 1 second you just did all three. So yeah.
Correct. Basically, we are only saying that we are eliminating one variable at a time and getting a new formula. That is all.
Right.
Once we have these all these formulas, then doing any word problem is very simple. So make a list of these formula on a page and then start solving questions. Let's begin with example 1. Okay, example 1. Can you please read the question?
Yes. A particle accelerates uniformly from 2 meters per second to 6 meters per second in 10 seconds. Find its acceleration.
Perfect. So whenever you read a question, you write down what is given to you, right? Now, before we
Okay.
begin, let's understand the term particle, right? So can you read this part?
A particle is defined as an object with negligible dimensions where the rotational forces and air resistance can be ignored. Mass of the particle is concentrated at a single point. All objects in our examples will be considered as particles.
Very important. So
Oh, okay.
whichever example we take, right? We say a bullet is being fired, a train is going. I know it's a big thing, train moving, right? Do you understand? We'll treat this as a
Yeah.
particle. We'll treat this as a particle. Means no dimensions, no air resistance, no revolution. You get my idea.
Oh, right. Okay.
Very important. In
Yeah.
this chapter, we say we fire a bullet. I know that the gun will be heated up with that frictional force, right? And the bullet goes in
Right.
down motion, right? Swinging all the way. But when we are doing the word problem in constant acceleration, we are assuming that bullet to be a particle moving without any air resistance, no rotation, nothing. You get my point?
Oh,
So
okay.
remember that
Yeah.
part. In all our examples, the object means a particle. So we may write a person running, train running, bullet running, whatever. It is a particle.
Well, is this just for your questions, or even in
Whole
like
chapter,
exams? If it.
whole
Oh,
chapter,
really?
whole
Oh,
chapter.
okay.
The assumption nobody writes it. I mean, it's never written there, right? But the questions are: the bullet is
Oh, right.
fired, and the train is moving, and this velocity, that velocity. Car is going with this velocity. Car is not a particle, but
Right.
for all our
You
examples,
assume it is.
all these bodies are treated as a particle. You understand?
Okay. So that's
Because
the key point, right?
people, we are talking about kinematics. We are not interested in the forces which are acting on the body at this moment. We'll take this up in the next
Okay.
unit. You get my point. Okay.
Right. Yeah.
So that's why I wanted to highlight this particular term before moving forward. And, that's very important to understand. So all examples, assumption is in your unit also, this is a
Yeah.
particle which is supposed to be of negligible dimensions. We cannot write zero, right? It's a point, correct? Where the mass is focused at a point and there is no air resistance in the movement. There is no rotations involved.
Okay.
Perfect. Now, apart from that, all other things is, as you know, initial velocity, final velocity, acceleration, and time. Only four things we have to work with, correct? So you can see
Right.
acceleration uniformly from means starting initial point. So u is equal to what? So you write, well, u is equals to 2,
2.
v is equals to 6, and delta t or t is equals to 10. Is that clear to you? And it
Should
says find
we?
acceleration. Yes. Ask.
In every exam question, when you do it, do you think it's best to write like Subat on the side and then
Yes.
fill in the letters?
Yes,
Okay.
yes. I have not written, but you have to write because I wanted to explain you. You have to write this first. U is this, V is this, delta T is this with units. With units. Okay.
Okay.
You
Oh,
put there. Okay,
right.
I have very limited space. I cannot be just writing each and everything, but I'm explaining it, correct?
Yeah.
So, and then substitute the values. Acceleration is rate of change of velocity, delta v over delta t, which really means final velocity minus the initial velocity from definition. And plug in the value 6 meters per second minus 2 meters per second divided by 10 seconds. Of course, seconds will cancel. You get, double up, square up, and they'll come down, right? So you get 0.4, that is 4 divided by 10 meters per second square as the acceleration. So that is your answer. Is that clear?
Right. Yeah.
So very simple. Can you please read the second example?
A bullet is fired straight up with the initial velocity of 400 meters per second. If it reaches the maximum height of 8 kilometers in 40 seconds, then find the acceleration of the bullet.
There are many things to understand in this. Of course, we now understand bullet will be treated as a particle. First. Second, initial velocity. So you write down what is initial velocity means. U is equals to 400. I'm not writing units. You have to write. If it reaches the maximum height of 8 kilometers, we are talking about displacement of 8 kilometers, and time delta t is given to us as 40 seconds. Find the acceleration A we need to find. Correct. So these are all the things given to us. Now, many times the information could be redundant, or we could use multiple formulas because, we have derived one formula from the other by eliminating some variables. Perfect. So what I noticed here is one more thing. We are saying maximum height of 8, right? So when a bullet is going to the maximum height, then it has to turn back, correct? So at turning point, what is your final velocity?
0.
So that is important to understand. Final velocity is 0.
Yeah.
You get the idea.
Yeah.
So you have to read carefully, understand what is implied.
Right, because that's not given in the question.
That's not given in the question. Okay. Yeah. You might like to use S equals to UT plus half AT squared to answer this question. You get my idea. You could do that.
Yeah.
You could do that with the information given. Okay. But many times this will also be not given. I wrote it for a purpose that you could use S equals to UT plus half AT squared and get the answer. But this is not given. Let us say it is not given. Okay. Then how are you going to solve it? You have to figure out that final velocity is 0.
Is 0. Right. Okay.
So you have to understand the question, right? Same question could be modified in so many different ways. Okay.
Yeah.
So I'm eliminating 8 kilometers from the question, and I'm now assuming that, well, it has to drop from there, and therefore final velocity should be 0. And I'm using that value in my calculation. Again, the same formula as in example 1, and that's why I've taken both the examples together, right? Many times you have to look for the values which are not directly given to you.
Right, yeah.
So acceleration is delta v over delta t, that is v minus u over this, and you plug in the values. What you get is minus 10 meters per second square. What does this minus 10 means? Can you explain me that?
Oh, I was gonna say going backwards, but that's not it, because it's not.
So bullet is being fired upwards. You see that? See, bullet is being fired upwards. You understand?
Right. Yeah.
But the acceleration is acting downwards, opposite direction, and that is why we have minus.
Oh.
Deceleration.
All right.
We also treat this as a deceleration. Final velocity is less than the initial velocity, right? So read this.
Yeah.
Read this, please.
The negative sign in the acceleration, referred to as deceleration, indicates that the final velocity is less than the initial velocity.
Perfect. That is what it means. Okay. So many times in the question, you may have to explain your answer. What is the meaning of your answer? That means you have to explain what is negative sign doing there.
Okay. So every time there's a negative sign on the acceleration, it means that the final velocity has to be less than the initial. You can use that as like a checkpoint. Okay.
Correct.
Yeah.
You apply brakes to stop the car. The final velocity is less than the initial, correct? That is what it is, correct?
Oh, right.
Yep. Now let's take another example. I hope you learned from this, right? I'm only trying to teach you a few things which are not directly written in the textbook, but we should infer.
Yeah. Final velocity is less than the initial. Okay. Yeah.
Third example. Can you please read this question?
An object is moving along a straight line from point A to point B with constant acceleration of 0.6 meters per second squared. The velocity at A is 4 meters per second, and it takes 15 seconds to move from A to B.
Yes.
Find the velocity of B and find the distance from A to B.
Correct. So what I would like you to do is, when you read such a question, sketch your
Mm-hmm.
diagram, right? So it's a very simple sketch. We just sketch a straight line here. Do you see this part?
Yeah.
We just sketched a straight line. And then we have taken 2 points as shown here as point A and B, correct? So this is your point A and that is your point B. Now at A, what is given to us? We are given the velocity at A as 4 meters per second. Perfect. From moving from A to B, constant acceleration of 0.6 meters square and the time taken is 15 seconds. So I've given all the information to you, correct? We need to find the velocity at B, right? So this is VB, which we need to find. That is your question. Now, from the given parameters, which is A is 0.6 meter per second square, delta T is 15 seconds, and initial velocity U is 4 meters per second. To find the final velocity, we'll use our first formula, which is V equals to U plus AT, correct? Substitute the
Yeah.
values given to you, and straight away, we get the velocity 13 meters per second at B, correct?
Yep.
So you got one part done, which is there are two parts to this question actually. First part is find the velocity, and then second is the part saying distance between A and B. So we've done A part, and this is the B part, distance. So S equals to UT plus half AT squared. Substitute the value, initial value of 4 for U, and time is given to you. Acceleration also is given to you. Figure out the answer, which is 127.5 meters. Is that clear to you?
Yeah.
Straightforward. So what the thing which we need to learn from here, that if we break down a movement into couple of movements, we can actually find the final velocities related to the initial velocity and continue this process.
Right.
The complicated questions come when they'll give you number of stations, right? At this point, at this point, at this point, and then you find the velocity at some other point. You get my idea.
Right. Yeah.
So this is the foundation for that kind of a question. Is that clear?
Oh, okay. Yeah.
Now let's look into that kind of question. Can you please read? Oh, this is a different question. Can you please read this question?
A car is traveling at 30 meters per second, which passes a stationary police officer. The police officer starts to move at a constant acceleration of 3.6 meters per second squared to chase the speeding car. To chase the speeding car 2 seconds after the car passes.
Yeah.
How fast is the police car traveling when it overtakes the speeding car?
Right. So slightly complicated question, very popular in examinations, right? So basically, let us say the speed zone was 20, something like this, or 25. A car was traveling at a speed of 30 meters per second, and at that point, he has to be fined, he or she. And then the police officer has noticed, but it starts 2 seconds after, and then we are trying to find how fast is police car traveling when it overtakes the speeding car. Now, the key point here to understand is the time at which the police officer will overtake the car, both the car and the police officer, I mean, both the persons have traveled the same distance, correct? They
All
have
right.
traveled the
Yeah.
same distance. So now we know that the car speed is given to us and time taken, let us be t. So we'll assume that both cars will be traveling the same distance. Of course, they will be because starting point for the other car is also same where the police officer was standing, correct? Now, police car will travel 2 extra seconds because the police car started 2 seconds after. So if t is the time taken by the speeding car, then the police officer's car will move for t plus 2 seconds. Clear?
Yeah.
Right. So let's find the distance moved by the speeding car. That should be 30 times t, since 30 is the speed and t is the time taken.
Right.
As
Yeah.
far as the police car is concerned, it accelerates. And the initial velocity will be zero because it was at rest, correct? So this part will be zero, initially rest. So this part is
Yeah.
zero. And then half at square. So half acceleration is given to us as 3.6 and time taken is 2 seconds extra. So t plus 2.
Yeah.
But both these distances should be equal, and therefore we get our equation to work with. Half 3.6 times t plus 2 whole square equals to 30t. The only
Wait,
variable,
where did that half AT? Sorry, where did the half AT squared go?
yeah,
That
half it,
that is that part.
this
All
is
right. Yeah. Yeah. You just sub the values in.
police car
Okay.
and speeding car. Both
Mhm.
have traveled the same distance, correct?
Right.
So therefore, we
Yeah.
will
Yeah.
substitute, and now we have a quadratic equation to work with. Since we have a quadratic equation, we'll just factor this or we'll use a quadratic formula as shown here, correct? So
Yeah.
you can expand, simplify, bring all the terms together, do all that. Then you get two answers, plus minus square root, right? You get two answers. One of them is not valid,
Mhm.
since you can always work it out.
Negative time.
Negative terms or anything which is less than 2 seconds, right? I
Oh
mean,
yeah,
it has
because
to
it
be
says
right.
right.
So we found that 14.4 is the calculated value. That is for the time taken, correct? The question was, how fast is the police car traveling? That means we need to find the
Add
velocity.
to.
So we'll multiply velocity with the time
Um,
taken. Yes, don't forget that part. And then write down your answer as 51.8 meters per second. Is that clear to you?
yeah. Yeah.
Very important question
Yeah.
from
Yeah.
any test point of view. Every time you have such a question. Okay.
Wait. So if we found what t was, then we don't need to find the t plus two because they're not asking for it. But if they did ask for the if they asked for the time that the police car was traveling, do you just add two to that 14.4?
Good point. Good
No.
point.
No. No.
Uh, now,
I'm not correcting you. I'm just
no,
asking.
no, that's a good point. I guess you're right. We should have taken t as the time taken by the if time taken by the car, speeding car is t, then overall time is t plus 2 when they intersect. So let us see like this. Let us say this is these that is the position, that is position A, and this is the position B. Correct? Now,
Yeah. Mhm.
uh, let's say that the speeding car, because to after 2 seconds, the police officer started. The police started after 2 seconds. So the time taken by the police officer is 2 plus t, where t is the time taken by the speeding car.
Right. So
So
you do use the 16.4.
yeah. So time taken by the
Oh,
speeding car was t, but time taken by the police officer is 2 plus t.
right.
And since that is the case, this t, because we're finding the velocity when
Of
the
the
police
police
stopper started.
car.
So definitely,
Right.
we took t plus 2 seconds, not t seconds. So this
Yeah,
t
because it's
should have been
repeating.
t plus 2. And
Right.
that is why
Okay.
we are using t plus 2 in half ut plus half at formula. The total
Yeah.
time taken by the police officer was the time t when that car moved additional distance, correct? And the police officer
Yeah.
had to catch for that additional distance, right? Which that car covered in those 2 seconds.
Right.
So
Yeah.
now
Now it
this
makes
should
sense.
be,
Yeah.
yeah, this should be 16.4. And then you recalculate. Can you do the calculation?
Yeah. So 3.6 times 16.4.
59.04.
59.04
We can write 59 meters.
meters per second.
Yes, thank you. I think
That's
that's
all
kind
right.
of critical because we have used t plus 2 in our formula. I think that's absolutely correct. Good.
Yeah, it's better when you drew the diagram. It made
Yes,
sense. Because
yes.
the speeding car went first, then 2 seconds later, the police car started. So you
Well,
have to do T+2 for the
T
police
plus
car.
2 is
Yeah.
the
I
time
was trying
taken
to
by
get it clear
the
in my head. Yeah.
Very good. You're a good student, I mean. Excellent. I overlooked
Just questioning things.
it. I liked it. Okay, now let's move on to the last question. Question number 5. Can you please read this question?
A toy train moves past 3 stations, A, B, and C, where AB is 4 meters and BC is 12 meters. The time taken to cross the distances AB and BC is 2 seconds and 4 seconds respectively. Find the velocity of the toy train at at A if the acceleration is constant.
Perfect. So this is similar to the previous example, example 3, but we have 3 different stations to work with, right? Now,
Mhm.
another difference is now you have to find the initial velocity, right? Earlier we were
Yeah.
finding the velocity at B. So these are the variations, and that actually covers up for most of the type of examples which you are going to come across in this unit. Perfect. So,
Right. Okay.
so that
Yeah.
will give you a good foundation on the whole unit as such. Perfect. Now, it is always important to make a sketch. In the last example, we did not do it and we did land into problems. You got my idea, right? So first
Right.
thing first, you'll see that I did not draw this sketch, right? And made huge difference. Earlier to this, while explaining, I mean, we had a sketch to work with. So a key issue in this is to always draw a sketch. Okay, it
Okay.
helps. Now, let us break this down into different sections. First section I'm calling it is section AB. So we have to see what happens in this section AB, right? So in
Yeah.
section AB, we have s equals to ut plus half at square. U is what we need to find, initial velocity, which is velocity at A. So now I'm using the subscript since there are many points and I will run out of U, V, and W. So I'm using
Right.
subscript, which is a better approach.
Yeah.
So we are saying velocity at A, acceleration being constant, and we're substituting all the given values to us. The given values are shown on the diagram. From A to B, the distance, or I should say the displacement, is 4 meters, and the time taken is 2 seconds. Substitute these values, but you get a relation between A and VA, right? So you get one equation.
Yeah.
Let's call this equation as our equation 1. So it's always a good idea to number your equations so that you can communicate better. Clear? Now
All
let's
right.
look
Okay.
into section BC. Yes.
Just wrote number equations.
Yeah,
Yeah.
number. Then let's look into section B to C. Now B to C, we can relate the velocity B with the velocity VA. So that is the relation. Initial velocity plus AT. Time taken was 4 seconds. So velocity at B is velocity at A plus 4 times acceleration.
Yeah.
And so we have a relation between this velocity B with the initial velocity A. Since we are interested in finding the initial velocity, it's a good idea to write all the equations in terms of the initial velocity. You get the idea?
Right. Yeah.
So I replaced, this was the formula, s equals to ut plus half at square. Use the same formula, right? Use the same formula, but replaced the velocity VB by velocity A
VA
and related term,
plus
4A, right? Acceleration to time.
right.
So that becomes your higher velocity because it's accelerating constantly. So you get a formula again, and this can be actually worked out as 3 equals to VA plus 6A, V at A at 6A. So that becomes our second equation.
Right.
You
So
just
now we've got two
expand the
equations.
terms, simplify them as shown here, right? And then, 12 was here. So first I divide by 4. So I got 3 here. And dividing by 4 cancel away this 4. Here we got 4 times 2 as 8. 4 square is 16. 16 divided by 8 is 2. And that's how I get 2a. Is that clear?
Mm-hmm. Oh yeah.
Yeah. So I divide by 4
And
at
now
this.
you've
Yeah. And then we rearrange and write it
and then you just solve simultaneous equations.
simultaneously. Yeah. So I did
Oh,
substitution.
okay.
Yeah. So we know what acceleration is from a. So we sub a sub 1 into.
Yeah.
and find
substitution.
velocity A, which is 1.8 meters per second. Is that clear to you?
Yeah, it was, yeah, very wordy ones, but yeah, these are the ones that are quite tricky because of the words. So like you said, sir, it's about breaking it down into little sections. And clearly, like you laid out here, section A, B, section B, C.
Yeah,
So we know what section we're like dealing with, and then find the relevant stuff in that area.
correct. So that is important. So now, even if the question is complicated, you can add a section and work on that. You gradually
Right.
you move from one
Yeah.
place to another. It's like a practical application, right?
Could I just ask
Yeah.
a quick thing?
Yeah.
Just to, because at school and stuff, my teacher's been ill like a lot, so we've been just kind of learning ourselves. So could we just quickly go to the like back to the basics of just position time graph, velocity time graph, and acceleration? And do you mind just showing me the relations between them? I know that you said like the rate of change in gradient, but like on a graph, could I
Yes.
just, yeah, so like this, if it
Yes.
was, yeah, do you mind just explaining it from position time to velocity and then
Okay.
velocity to
Now
acceleration?
let's look into the position time graph. This is our position time graph, right? The third one. Third one here is the position time graph. So let me just
Yeah.
remove the highlight from here. And now we are working on the position time graph, which is shown here in this fashion, right? Forget for a moment whether it's quadratic or nonlinear, whatever. The idea is
Okay.
from position time graph, we want to get the velocity, right? So how do you convert from position to time graph to velocity time graph, right? That is your question probably, correct?
Yeah.
So in that case, what you need to do is you get different points. And at different points, you draw tangents. So for example, we have the initial point here. If I draw a tangent line here, it is a horizontal line. So at this horizontal line, the slope, which is rate of change, is zero. You get the idea? Because velocity is
Because it's, yeah.
basically, velocity is basically change in rate of change in position, correct?
Yeah.
At this point, we notice that there is some positive gradient, and then the gradient is increasing. Do you see that? So these are different gradients.
Yeah.
Let us say this gradient value is 1 and this is 2. Then you plot these points here on the graph and connect them with the line. So once you do that, you get your VT graph.
Oh, okay. When you explain it, I get it. And then when you go, I don't. So can I just take a picture of that?
Yeah, sure.
Okay. So what you're saying is we have a position time graph, whatever like curve there is on there, all you do is find the gradient on there.
Yes,
And if the gradient is 1, 2, 3, something like that, those are the points that you plot
correct.
on your velocity time graph and
Yes.
then join out. Oh, okay.
Perfect, perfect. So that is how you do it. And in case the velocity time graph is non-linear, let's take a case, right? Let's take a case. So in case the let's say position time graph is something like this, let me sketch one, right? So this is acceleration is not constant, right? So in that case, what do you notice? You notice that in this part, velocity is positive, right? In this part, velocity is zero. And in this part, velocity is negative. Here again, it is zero. And then here again, velocity is positive. Do you see that part?
Yeah.
So that really means when you plot this diagram, since it is zero, you will get a graph which will be kind of like this, VT graph. So rate of change for a cubic function will be quadratic, which you will get as
Yeah.
shown in orange. And now, if you find the rate of change here,
Oh,
yeah,
yeah.
if you find the rate of change in this particular case, drawing each and every graph, which I'll just do it in a minute. I'm using a different ink now. Right.
Oh,
So if I draw a gradient here, that means acceleration is negative, right? If I gradient here, acceleration is
it's
zero,
positive.
and A
And
is
then,
positive. So that means I have a straight line here, right? Which is negative here and positive there and zero somewhere in between. So maybe let me just draw like this, x-axis. Is that clear to you?
oh, right.
I should say
So
time.
that makes sense when it's ringing, it's clicking back to when we did like calculus and derivatives, because every time you like go past the degree of the polynomial decreases. So we went from a cubic to quadratic to linear. Oh,
Linear, yeah.
okay.
Now when we go
Yeah, now
back,
it's clear. Yeah.
Clear? When we are talking about
Yeah.
constant acceleration, this the constant acceleration, we are talking about acceleration is constant,
Hmm.
velocity is linear, and position graph will be quadratic. 1 degree higher,
Right.
one
Okay. Yeah.
degree higher. Another
Yeah.
thing you must have noticed is look at this formula which we derived. What is the formula? Displacement is ut plus half at square. Do you see the
80.
t square thing?
Oh, the t squared.
This is
Oh,
quadratic.
so it's quadratic. Oh, okay. So
Velocity,
there's everything there, like to help you. Oh, it's a linear function.
linear function. T, y equals to mx plus
Oh,
b. Y equals to mx plus b. Exactly same equation. You get the idea, right? So that
yeah.
is what it is. So basically, constant acceleration is chapter like linear equations, right? More or less.
Yeah. All right. Yeah, that's nice and clear in my head because I'm always finding it hard. Like, how do you, from a position time graph, how are you plotting a velocity time graph? Why, how are you doing it so quickly? Now it makes sense because I know I got it was to do with the gradient. I just didn't know what you were plotting because you're plotting the gradient points on the graph.
Yeah.
Yeah.
The
Okay.
next
That
very
was the light bulb moment.
correct. Next very important question here is how do we get from velocity time graph to displacement?
To displacement time graph
Yeah,
or
good.
just displacement?
Displacement time graph also. Yeah, we could do displacement time graph. So you do it by finding the area under
How
the
do
curve.
we, but
So
how do you plot that?
okay, you can find different displacement. Let's say from here to here, correct?
Yeah.
So you know displacement 1 unit is this much, correct? So you get a point here. Then you work out displacement for this much, right? You get a point there.
Yeah.
And you can see that it will follow this path. We'll take this up in the next lesson. Is that clear?
Oh. Yeah, so every time you go a long time, and then let's say the area was whatever you said, you just plot that where the position is, and then it'll keep going higher. So if you join other points, you would still get that quadratic.
Yeah. For that particular time, we'll have the displacement. For this particular point, we'll have the displacement. You get a point there. And then you connect these
Right.
points to the quadratic relation.
Yeah, yeah, yeah.
You get the idea, right?
Is
We'll
that the only link? Do you have to find area under? You can't
the
find the area under the acceleration. Huh?
area under the velocity graph will give you displacement.
Yeah. Yeah. Is that
Any
it?
velocity.
No other areas.
Yeah.
Oh, okay.
With the
Okay.
x-axis. And always display, yeah, I mean, we could work this out. Is that okay? So we'll do that in the
Yeah,
next
that makes
lesson.
sense.
Yeah.
Cool.
Amy,
Well, thank you
can
so
you
much, sir.
summarize, can you summarize our learnings today?
Yes, I can. So today was a bit of a more word problem kind of based questions, and I just wrote a few key points on like what we kind of learned and stuff. So in the beginning, we started with a formula. Um, Oh yeah, this is the page. And then on the second pages, even though you've got it all listed out for you, we just derived them just to show like
Yes.
where you got it from and how yeah you got to the questions. So yeah, the v equals u plus at was the simple, just knowing acceleration is the rate of change of velocity. So that's how you figure out this one. And then the other three can be found using the first equation that's highlighted in the box where s equals just distance equals speed times time kind of thing. So you just find the average velocity times the time. But we said the average velocity in the previous one was the initial, add the final, then divide by 2. So then you just keep subbing in that value, and then like you do, which we've shown for these three, you kind of eliminate one by one between the boxed equation and the one you're trying to figure out, and just keep doing it like this, eliminate all the values, and you get the 3 different equations. So that was simple. And what I talked about in the beginning was that the last equation, s equals vt minus half at squared, you still do need to find u. That statement still stands, what you said. It's just that you've subbed in v equals as u plus at into that equation. So you still need to find u either way. So we've just like eliminated it for that. So don't think that we've completely like ignored u. We just subbed it in. So yeah, it's the same thing. Then with the exercises, what we found out was when doing this, always first draw a diagram, because it helps completely just trying to understand like what's actually happening. And like we saw in this question, some of the values of the SUVAT will not be given, but you should infer that from the question. So like this one, when we said the bullet was being fired up and then it comes back down, that where it reaches that highest point, the final velocity would be 0, but that's not stated in the question. But you need to know that in case some of the SUVAT stuff aren't given. Like if you took out the 8 kilometers, you would have like even less variables to work with. So that's important knowing that. And then whenever you work through any of these word problems, just remember that the object you're dealing with is a particle, and that's just understanding that no other forces act on it, and the mass of that particle is like focused in one area. So just keep that in mind, because we do know like the train, person running, all these things are not particles, but for these questions you have to assume that. So that's important. And then second one, again, yeah, we talked about this diagram, breaking it up into sections, and how each kind of point has a certain time and velocity in each of the sections. So the diagrams are so helpful. Like I can't stress that enough, because you can go a bit wrong if you don't. And then question 4, I really like this, because even though after we went through the question, after the like analyzing a bit more and actually understanding what was happening, now it's like thoroughly clear. Like if I see this question again, I know exactly what to do, because I know if a speeding car went in front, that's the time taken we say as t, then the police car would have started 2 minutes after, so that would be t plus 2. So remember to when you said in the beginning, sir, numbering your equations, numbering your variables, and clearly stating what the different objects in the question is talking about with their variables. So I think just writing on top police car t plus 2, it's clear, so that you won't get confused between which values you're going to sub in and things.
That is so true.
Yeah. And then the final one, yeah, that was just again one of these section-based ones, breaking it up into different sectors and working in those areas. So yeah.
Perfect. So I hope that really helps, Emmy. As we discussed,
Yes,
we'll now discuss velocity time graph in our next lesson and see how do we work with velocity time graph. That'll be great. And we'll not keep the restriction of acceleration being constant. So we'll make it more flexible. So we'll be ready for the next unit, which will be dynamics. Okay. So that'll be between the 2 units. Very important one. Perfect. So practice some.
Thank you so much, sir.
Yeah. Okay,
Thank you.
Bye and all the best.
Yeah, have a good rest of your week.
You too. Thank you.
Thank you. Bye.